It would be nice if we could mix both approaches, use Perfluent Open API to get kernel and native stack traces and to make use of hardware performance counters, while for Java part rely on async get call trace API, which works pretty good, and it knows how to work interpreted frames. And exactly this idea was implemented in Async-profiler. It uses Perfluent Open API directly without relying on perf. So it uses this API to receive stack trace samples from the kernel and Java stack traces from async get call trace. The tricky part is how to merge these two stacks. Who is interested in implementation detail, please ask me later. I'll be more than happy to talk about that, but it will take some time. So, Async-profiler. This is a no.
Yeah. Sorry, Andrei.
Sure.
It's Catherine. There are a couple of questions. I think maybe I just want to leave it up to you. Oh, sorry, Yvonne, because a couple of them are about the flame graph.
Yeah.
And do you want to hold them and wait to come back? And there's also some other questions.
It's okay to ask them now.
You want to? Because for the flame graph, you might even want to flip back to it. I'm not sure, but Nikita was wondering about the long x-axis. Does the long x-axis mean the long time of execution?
Yes.
And he also wanted to know if you could show them how to find something bad in the flame graph. You knew this was going to happen because that flame graph is the most beautiful thing ever.
Yeah, let me cover it shortly now, and there will be many flame graphs further in my talk. So, okay, here, yeah, the larger is, the longer is the rectangle. It means there more time this method was seen during sampling. So, for example, the main method was seen 85% of time, and it's completely understood because the main method executes all the other logic for application. But what is usually interesting when analyzing flame graphs are the leaf frames that do not have other frames on top of them, and the longest such leaf frames can be a sign of the problems. For example, macho reset in this case. Basically, such rectangles mean that these methods have a big, large self-execution time. So they are obvious hotspots. Okay, more questions?
Yeah, there are. So I just want to throw them out because I know you're going to get a zillion questions. Earlier, when you got started, there was a question about Async-profiler working. How does it work only with some JVMs because it uses a hotspot specific API?
Yeah, absolutely.
That's why. And
hotspot private API, async get call trace, but well, it's the most popular JVM, and so pretty much everyone uses it. Also, actually, Azul Zinc JVM also supports this API, and Async-profiler works with Zinc as well.
Oh, we're well familiar with them. So, you know, as a follow-up to that, Sridhar was wondering, is that why other profilers haven't been updated to avoid the safe point bias? Do you think that's why other profilers aren't updated? Is it to avoid the safe point bias?
Yeah, the main reason is that this is non-standard API, but as far as I know, for example, your kit already supports async traces as well. And as far as I understand, it also relies on async get call trace.
Okay, so just to close the loop, I'm going to jump a little bit forward. I didn't want to lose track of that question, so it was a little bit out of sync, but I think it sets a nice stage. Sridhar also wondered, after you went through the flame graph, if there's a way to profile any specific Java threads to reduce the profile size. I'm just going to throw that one out there, Andrei, and I'm thinking you might want to hold that till later, but it's up to you. I hate to be the one to decide because I have no idea.
Yeah, it's possible. We'll get to it.
Yeah, that's what I was thinking. Okay, so I see that somebody put a question in the chat box, and I'm going to ask people if they could just throw them into the Q&A because it's so much easier to moderate that way. So I'm going to type to him because I'm killing his name. So I'm shutting up.
Vyacheslav Kiro Urker.
Yeah.
So please put it on GTK. I think, yeah, does flame graph work with any GTK? Is a flame graph is just only, I think, just presentation of some data. And so we'll take it on the Q&A.
Yeah, okay, great. Thank you. Back to Andrei, right, Ivan?
Yeah, please go on.
Beautiful.
So, Async-profiler is an open source project available on GitHub. You see it's a live project. It has the recent version was released just a few days ago. I'm not the only one who develops it. There are at least 33 people who somehow committed their changes to the project, and importantly, it has a rather permissive Apache 2 license, so feel free to use it. And right there on the project page, you'll find the links to pre-built binaries for many platforms. Not many, just Linux and Mac, and some popular architectures. By the way, recently Apple announced Macs on ARM processors. So if someone buys me a ARM Mac, I promise to add Mac ARM support to Async-profiler. Well, never mind, just kidding. Okay, when you extract the package, you'll find a bunch of files there. So this core profiler agent and a helper binary that allows to attach this agent dynamically to a running JVM. So you don't need to start a JVM with any special options in order to profile it with Async-profiler. So thanks to JAttach, it will be possible in runtime. But as I told earlier, if you plan to attach profiler later, it will be wise to add debug non-safe points JVM option to allow more precise inlined frames in the stack traces. So the shell script, which is a command line interface for the profiler, and Java API to use it directly from your applications, and couple of standalone converters to convert between formats supported by the profiler and external tools. and the most important part. So everyone forgets about this one, but the important section there is troubleshooting. So if you hit some problems with running using Async-profiler, make sure that if it is listed in README or not. If not, just go to GitHub and post GitHub issue. Okay, the most interesting part. Let's see it in action.
Yeah, I'd like to mention, you said please welcome to use the Async-profiler, but I think also welcome PR against it. If you see anything that you could, how can you improve that tooling?
Absolutely. Okay, let me remind about this string builder test. I'm going to run it and yeah. So I use a command line interface of the profiler. So the main options are -d, 5. This means I'll profile for 5 seconds. -e, event, profiling event. What I want to profile is CPU. It's a default event, so I may just omit it. And output file. Let's say out HTML. If the output file name ends with HTML, the profiler will automatically generate the flame graph when it ends profiling. And the process ID. But I don't want to find the process ID. It's possible to name it, to put here name of a Java application, and the script will find the process automatically. No, it will. Oh, yeah. So what will show Async-profiler? Here's flame graph for our string builder test. And it says that almost all time is spent actually in array copy called by string builder delete. And this time, I believe the profiler, because every time you delete 5 characters from the beginning of the string builder, we need to move the whole million characters to the beginning of the array, and that's definitely takes time. Okay, what about other example, a socket test with busy client and idle client? I also profile it for 5 seconds. Also, if I have only one running Java application, I don't even need to put its name. I can just put GPS keyword, which will mean that the process ID will be discovered automatically by the profiler script. So from now on, I will use GPS as a shortcut. So as to our busy and idle client, we see no idle client here, but yeah, there is a busy client and the reader, and the main method, the writer. I will post the complete code for my examples later on. Another interesting thing that we see in this flame graph is that it shows that significant amount of time is really spent in Linux kernel code, the brown part of the graph. And it's quite understood that our Java application doesn't do much, doesn't do business logic, just sends and receives. So the most time is spent in this GCP stack. But why a regular Java developer needs to know about this low-level stuff? Actually, this helps pretty often, at least in our practice. Consider this simple example. So you're reading a file using a regular Java API, file input stream, read it using a heap buffer. Which buffer size to choose to achieve the best file I/O performance? My first idea was to choose the largest buffer. So the larger is buffer, the less number of system calls we do, and more batching. So the large one should be good. But it appears that in this particular case, on my system, the 16 megabytes was best. To find out why, I started profiling this code with Async-profiler. So here what I got with 32 megs buffer. And what I found here strange is a large number of page faults. And once I reduced the buffer just by 1 megabyte, all this page fault part completely disappeared from the graph, and the performance became, the throughput increased. And the reason was that the standard system allocator had a threshold of 32 megabytes. Well, you see that the example writes sorry. So we use a heap buffer for I/O, but JVM cannot write directly from heap to a socket. So it needs an intermediate buffer in native memory. And it allocates this intermediate buffer and using the standard system allocator malloc. And the malloc has this threshold. Actually, different implementations of malloc on different systems may behave differently, but on this particular system, there was a threshold of 32 megabytes where memory allocations were done directly from the operating system by asking new memory pages from operating system. But for sizes below 32 megabytes, malloc was using its own native heap. So here was the difference come from. Another example, which I already encountered several times, is a strange behavior of system nano time. One of my colleagues wondered that when he upgraded his PC, discovered that all his benchmarks suddenly became much slower. And the reason was that the nano time itself became much staller. If you profile using the Java profiler, you will not see the difference at all, because the stack trace ends on the Java method nano time. That's it. But the clue is hidden inside the Linux kernel. So in a good case, in a fast case, there was no kernel part of the stack trace at all. And in bad case, there were many system calls, real system calls, highlighted by brown here. And of course, system calls are slow. and Googling for HPAT. What is HPAT? Discovered that there are multiple available clock sources in Linux, and the fastest one is TSC, and there is optimization in kernel to read clock source, to read the TSC clock source. So to get a timestamp, you don't even need to call into kernel. You just use special VTSO object, but this separate topic. I will not get into details. Just wanted to let you know that there are different clock sources. And for example, if you run applications on Amazon EC2 using Xen virtualization, so be aware that the default clock source there is Xen, and you can experience the same problem of slow nano time there. And so by following the link, you'll find a post how to tune the clock source on EC2. Another example is that with next Java update, it was a couple of years ago when Java 10 was released, and it appeared that random access file.setLength became much slower. And again, without digging into kernel code, we couldn't know that the problem is there. Actually, the implementation of random access file.setLength became to call a different system call, which is much slower. And this was a GTK bug, which was fixed then in GTK 11. But again, without looking deep into our system, we wouldn't know that. Okay, any questions about this part?
Yeah.
Oh my gosh, you have a ton of questions. Ivan, can we start with the most simple question? Because I think the other questions we might want to hold. The simple question is, do you need super user privileges to run the profile, since it uses perf events? That's a simple one from Timur.
Well, some kind of.
Oh, it's not simple.
It's not necessarily. The root privileges are not required to run perf. Actually, I have this somewhere at the end of my slides. Oh, yeah, myths and facts about Async-profiler. So first of all, the misconception that I hear too often that you need to install perf in order to use Async-profiler. This is not true. Async-profiler doesn't use perf utility, but it relies on a system call which exists everywhere in all Linux kernels, starting from 2.6.30 something. It doesn't require root privileges. However, in order to use perf events for being not privileged user, you need to probably need to tweak some kernel system CTL options. And the similar problem with containers. Yes, I think Async-profiler can be used in a container if you adjust the default seccomp policy, or even if it's not possible in your case to adjust the policy, it can fall back to different profiling mechanism which doesn't rely on perf events, but relies on a system timer.
Ivan, do you think we should hold the other questions for later?
Yeah, I think so. Andrei, my understanding, we're heading to the end of the first part, right? So once
Okay.
you're done, we'll cover the rest of the questions, and then we'll have a small break.
Okay. So.
Yeah, and we should let people know that when we have this small break, don't disconnect. Just walk away, check your email, get a drink of water, but don't disconnect. Come right back in a couple of minutes.
Yeah, I couldn't help putting one marketing slide in my technical presentation. So it basically compares the approaches to Java profiling, which I talked about earlier. And well, as I told, Async-profiler tries to get best from both approaches. And well, but CPU profiling is not always helpful. For example, for measuring application startup. First, because you can't afford connecting profiler at runtime, because you want it to be attached from the very beginning. So there is an option to start Async-profiler as an agent right with the JVM start. And another problem is that CPU profiling doesn't always show why your startup is slow, because not the time is not always spent doing some CPU intensive work. Otherwise, an application may wait for some disk I/O or accessing a database. I don't know, in waiting on some logs. And here, here will wall clock profiling help. So what is wall clock profiling? It's a technique where all threads, no matter what they're doing, either they're in running state or just sleeping on some lock or just in thread sleep, so they are sampled equally. Async-profiler does have support for this mode. As an event, you parse -c wall. It's usually convenient to run wall clock profiling in threaded mode, where all threads are profiled separately, because you typically want to know what each particular thread is doing, and you're not interested in, let's say, garbage collector threads or compiler threads or threads in a thread pool, or threads that are sleeping in a thread pool. So when running profiler using a script, these are options on the left, and their corresponding options for running the profiler as an agent. And let me show it in action. So I'll run typical classical Spring example, vet clinic. So here I attach profiler right on the JVM startup. I specify profiling event wall, threads, threaded profiler, and where I write my flame graph. And the rest options usual, just like you run applications normally. So here is my application starting. Starting. Okay. 28 seconds. Too much. Let's see what it was doing. Here's a wall clock profile. So you see separate bars for each thread. These are names of the threads. As I told that most threads are not interesting to us, like GC threads. But here's the main thread. And so we can see what it was doing. And here we will not only see a CPU intensive fork, but also like waiting time. Here we spent 9% of time waiting on some logs. We can zoom and see what are these logs. In this case, this is actually a log inside the JVM. Yeah. During class loading. You can also see how much time is spent reading bytes from a disk for a large amount of time. Again, CPU profiling will not show you this. A particular case of profiling logs. Well, when there is a contented log in your application, a log that is acquired simultaneously by multiple threads. So some time is spent on acquiring the log, and this time can be sometimes can be really large. And using Async-profiler, it's possible to measure this time as well. So there is a special mode. You need to specify -c log event, and the flame graph can be generated in two modes. So by default, it will record each sample of log contention. And if I instead specify flame graph equal total, instead of counting samples, it will count the amount of time spent on acquiring logs. And the same is true for not only for Java intrinsic logs, but also for reentrant logs from Java util concurrent. Again, let's see it in action. This is a test which sends UDP datagrams in multiple threads, just in localhost. Let me show you this. Let me show you the code. It's pretty simple test. So it starts 10 threads, and all these 10 threads doing are running send loop and counts total number of packets sent. That's it. No actual network transfer using just localhost. So in this case, we could send just 50,000 packets per second. In my opinion, it's too little for 10 threads sending continuously. And let's profile it with our log mode. So event log flame graph total to record the amount of time spent acquiring logs. Just 5 seconds will be enough. And what we'll see that 10 threads together spent 44 seconds just waiting on logs. And the reason is that the datagram channel implementation acquires a log. So it's not possible to send datagrams in multiple threads just through one channel. So they will serialize on this one log.
I'm sorry, Andrei. How did you know that it's 44 seconds?
Do you see this large number in a
Yeah, but
pop-up window?
it says samples. So samples in this case, it's nanoseconds, right?
Yeah, because I specified flame graph total. It's actually the total number of nanoseconds. But yeah, the flame graph enter doesn't make difference.
Okay, got it. Thank you. And I'm sorry, a little question. If without that total parameter, we'll see only how much time we hit the log.
Yeah, exactly. So we can do it, no problem. It's will not take too much time.
Yeah, just to give people a flavor.
Yeah, exactly the same shape of the graph, but now you see just number of samples without total time.
Thanks.
Okay, so what to do with it? And interestingly, that even in the recent GDK 16, this log is not fixed, which just sounds weird, nonsense for me. And that's why we in Odnoklassniki use our own networking library instead of Java NIO. Well, who attended my other conference talks probably already know which library is it. It's called one NIO. So the same test. Let me run the same test. Oh, much more. So almost three times more packets. Yeah, 3 times more packets. But the code looks exactly the same, except that instead of datagram socket channel, we use a socket from one NAO net. Okay, questions on this part, and we can make a break.
Yeah, thank you.
Ivan,
yeah.
You want to take a look at the Q&A because there are quite a few. Like Sridev's last question that came in, I don't know if you want to start there or how you want to do this. Maybe Andrei even wants to look in the Q&A box and see.
Yeah, and pick up the easiest one and choose the questions that you think would be wiser to move to the extended Q&A session. Yeah, I think the question about merge stacks and AGCT will definitely cover later. Just go ahead.
Yeah, there was a question really early on from Shridev about whether there's a way to profile only specific Java threads to reduce the profile size.
Yes, there is there are two options. First, Java API, which allows to profile you only the given threads, but it works only for walk log profiling. For all other types of profiling, you may use filters there. I will show filters. I hope you will have time for me to show filters later on. Oh, how does Async-profiler merge stacks? Well, it's a large topic, but in short, I attach. There is a possibility to bind perf event to a particular thread. So I make a separate perf event for each Java thread and make it process signals only on this thread. This way, once signal from profiler happens, it is processed immediately, almost immediately, by the same thread that generated the signal. And then in the signal handler, I call async get call trace. First, I read a sample, native stack sample from the ring buffer, and then call async get call trace to obtain the Java part of the stack. And actually, if there are no concurrent signals, then operating system guarantees that the signal will be delivered exactly when it happened. So that's why I can merge these two parts. So which next question from Nikita: on which operating system have you found a good buffer size? It's 32 megabytes. Well, I said that 32 megabytes wasn't a good choice, but on Linux with a standard system allocator from libc on CentOS, in my case, 16 megabytes was good. Does C Linux affect Async-profiler when enabled? Well, C Linux can be used to prevent perf event open system calls, but all Async-profiler needs is to enable perf event open syscall. So you can allow to call. You can allow this syscall in C Linux, seccomp, and Async-profiler will work. Is there an overhead to using Async-profiler as an agent versus command line? Not really. There was a big problem of earlier where Async-profiler, when launched as an agent, significantly the startup time of an application with that loads lots of classes was really bad, and this was actually a JVM problem in JDK 8, but I found how to work around it with Async-profiler. So if you take the recent version of Async-profiler, there it will be fine. So in our production systems, we start all our Java applications with Async-profiler enabled, not turned on, but just enabled as an agent. Some of applications are idle most of the time and process events as they arrive. We are interested in minimizing the events processing time. How can we isolate and measure that using Async-profiler? I will have exactly this example later on. So to get the seconds on flame graph, we should pass total parameter right.